Marina, dovremmo essere... Dai una chiamata tu fuori? Il corridoio, perché mi sa che c'è un sacco di gente. Dai fai una chiamata in corridoio.
Che c'è che mi va?
Sì, un minuto
e arrivo.
Partiamo. Quarto d'ora. Funziona lo stream? Qui noi risultiamo online.
Io la vedo giusto.
Sì.
Che non la ricordo ancora. Sì.
Okay. I think we can start again. We took our 15 minutes plus of break. So the afternoon session, it's the second session of this young researcher meeting, and is about matter physics. It's the first session about matter physics. We will have another one tomorrow. And we are going to start with Laura Fazzi from the University of Ronto Vergata, that will speak about stretchable conductors made of single-wall carbon nanotubes, self-graph tip on polymer films. Thanks.
Thank you. Good afternoon, everybody, and thank you to the organizer for the opportunity. And yes, I would like to talk about stretchable conductors made by single-wall carbon nanotubes on polymer films. Yes. A brief summary. I would like to introduce why we need flexible and stretchable materials, the characteristics of single-wall carbon nanotubes polymer composite materials, and different kinds of polymers for different applications. We will see a wide range field of application of these devices and conclusion. Okay. Why are conductive flexible materials? Because now we need electronic devices with us every time we would like to dress our devices. So the flexible conductive materials now is a reality. I don't know how much is the cost of this, but there is a limit on back. So the flexible materials, conductive flexible material now is not is a new thing, not is a new materials, but now we would like to improve and go to a flexible conductive, stretchable conductive materials. Why? Because we want to have conductors and a sensor that can be stretchable and moldable to dress, to implant. This is in particular an application of a sensor devices to detect the electrocorticograms from the rat's brain. But I don't want to talk about because Anna Periello will talk you, and she will show you this specific application. But I want to show you these kind of materials. This is a polymer film. In particular, this is a polyethylene film, about 20 microns, with 2 tracks of carbon nanotubes. You can see that happen a particular thing. This is self-grafting. You can see a relaxing and little stretched materials, and you can see that the carbon nanotubes are inside and graft the polymer. Okay, what is the principle of CNT polymer self-grafting? Is this? I want to show you. You have to imagine this substrate. This is a moldable substrate because the polymer is heat near the melting point. And this is a bundle of carbon nanotubes. When you put, with the drop casting, carbon nanotubes on the polymer, you can obtain this. I can flex and stretch and obtain a conductor that resists of the strain. Why not use chemical functionalization? Because it's more complex and more expensive. We would like to obtain a final goal to have an inkjet printing carbon nanotubes for low-cost mass production of stretchable composite materials. So the low cost is an important point of this research. This is scanning electron microscopy images, and you can see the substrate and the tracks of carbon nanotubes. And we can see that when we stretch the device, we can break. But if you see here, you see that carbon nanotubes inside remain connected, so the resistance increase, but is still conductive. So you can use this for this kind of application in which you can stress and stretch. This is 2 parts of the conductive in these composite devices, in these composite materials. An external part that is thick and is the conductive part, the most of the conduction go through this part. But if you broke or remove this external layer, remain an internal layer that still remain conductive. This is the idea. So let's go to characterize our devices, our materials. You can see a simple. When you applied a voltage, you can see the relation between current and voltage. So this is an ohmic-like conductive, ohmic-like conductors, and you can see that when you strain and change the length of the conductor, in this particularly results is for polyethylene film. You have an increasing of the resistance, but you can use this change to have a sensor, but we will see in the next. This is a particular study of the viscoelastic properties of the naked medium density polyethylene that you can see here, pink. The black is the composite material, and is possible to see that when we put on a single wall carbon nanotubes, we give strength of the materials. So we change this slope. That this is in particular the part, the elastic part, and this is the plastic part. But the important result is this, that the resistance increase when the polymer is in the plastic part. After this change of slope, So when the substrate isn't elastic. So if we change the polymer, we change this kind of slope, the elastic and the plastic, and we obtain different resistance versus strain behavior. And we can choose the behavior that we want for our devices, for different applications. So we would like to understand the behavior in frequency response, because we want to use to record an electrocorticograms. So we need that there isn't anything in this region. In particular, we see that under of megahertz, we haven't problem, and generally the brain frequency are here, so we haven't problem. Okay, but we would like to study the temperature response, to study the Joule effect, and we can see this, that we haven't problem under 50 volt, and here when you see, when we are near the melting point of the polymer, the composite material broken, because this is the polymer that is near the melting point. So, but carbon nanotubes haven't problem. Okay, and why comparison among polymer? Because the change of this slope permit us to choose the correct polymer and the correct strain resistance response for different application. You will see this is a natural latex rubber, and you can see. Oops, I think that's. Okay. You can see the resistance in function of times when you change the length of the device, and here the resistance in function of length. So you have the strain, add the stress and the strain, and you have a change of resistance. Why this? To have this kind of application, like strain sensors, pressure sensor, stretchable electrical connector, 3D printing circuitry, biomedical application, electronic meninges, prosthetic heads, artificial bladder. You can see this is the Morandi bridge. You think at the Morandi bridge with a fast strain sensor and cheap and fast strain sensors, or this can, for diabetic feet, when you have some problems of your feet, you have a pressure sensor under your cloth, and this is the future. Could be an artificial meninges to obtain a connection with an arm that can move, or some kind of problem for the neurological connection. So this is a very wide field of application of these stretchable conductive materials. So, in conclusion, we have a new method to obtain a robust, stable, and stretchable composite materials. And the same analysis has shown that there is a grafting inside, so it's so stable. And the electrical and the viscoelastic characteristic of the carbon nanotubes and polymers give us a very big kind of opportunities to use, and is possible to a very different application of this kind of new materials. So, okay. Thank you.
Any question from the public? Okay, 1, 2.
So I have one question and one curiosity. So the first one is, did you ever probe the fact that your carbon nanotubes are actually single-walled or not multi-walled carbon nanotubes?
No, we tried single-wall and multi-wall, but the grafting of single-wall is very stable in contrast of the multi-wall that tend to remove, and because it is so big to enter in the polymer chains.
The second one was, have you ever tried a multi-walled graph?
Yes, yeah, we have tried, yes.
Thanks for your interesting presentation.
Thank you.
Mine is more curiosity than a question. We have seen in the stress elongation graph the plastic phase is extended, no?
Yeah.
But just a curiosity, where is the breaking lead?
The?
Breaking lead. You break the cell.
No, okay, yes, but we have different slope for different polymer. This is the polyethylene, and we can go, I don't remember if 200%. But depends on the polymer film that you use and of the thick of the polymer film. So.
Which one do you address first?
The polymer. Yes, the polymer. Yeah. The polymer. The superficial layer of the carbon nanotubes can be broken, but seem to be a squeeze box. Okay, and the connection inside the polymers still remain. So there is the resistance change, okay, in function of the length. But if you say in your range, in particular for the application that Anna Fioriello will show you, this is a particularly polyethylene film to have biocompatibility and have a plus and elastoplastic behavior to move these devices inside the brain from dura and pia mater, in the brain of rats.
Thank you.
Okay, I have one more curiosity.
Yeah.
I can see that there are really a lot of applications. I can imagine, for example, clothes.
For the space, no.
For space.
Okay.
No, I was thinking about clothes with every kind of
Yes.
sensor inside.
Yes.
But what about the aging? Are these reliable in a time scale of years, or do you have to change every now and then the sensor inside your?
We don't know now, but now we say to obtain a machine to study the aging, like the IKEA movement for the same, more or less, to understand the stability in long time. We don't know now, but we are studying.
Okay, thanks a lot, Laura. Now we have Imran Khan. Last 5 I pull 15 minutes. The last 5 minutes. I pull the last 5 minutes.
Good afternoon, everyone. Yeah, my name is Imran, and I'm going to talk about the generation of green laser beam that we are producing in a single pass second harmonic generation to a nonlinear crystal, which is periodic lithium hybrid crystal in our case. It's better now. So we have the single pass second harmonic generation of 1064 nanometer laser, which is a pump laser field in our case, in a periodically poor lithium hybrid crystal, and that green laser beam which we are generating will be used as auxiliary laser for the advanced gravitational wave detector. So just briefly discussing about the gravitational detector is, the LIGO detector is a kilometric long arm length interferometer, where the two arms of the detector are 3 kilometers long each. And we are able to see these tiny ripples in the fabric of space-time, which we call gravitational wave, using this kind of interferometer that allows us to detect gravitational waves. So what we actually look for is the displacement in the test masses of the detector, which are mirrored in our case, and that changes when gravitational wave passes by the detector. So there are already a network of detectors currently active, and they are also ready to observe gravitational waves. And there are a few more which will join in future, like some of them are under construction, and one of them is in planning state. So in future, we are hoping for a network of gravitational detectors across the globe that will allow us to pinpoint the sources better outside in the universe. So in the very first detection of gravitational wave in September 2015, now gravitational wave offers a new window in astronomy, where we have at present some ground-based detectors that allows us to detect gravitational wave in a certain bandwidth. But in order to go further lower in terms of frequency of the gravitational sources, there are plans to have a new kind of detector in the space, that is the laser interferometer space antenna LISA, which will for which the research and development activities are in progress, and in future we are hoping that at some point LISA will also join this network of detectors to further strengthen the field of gravitational astronomy. So this talking in detail about the detector itself. So it's composed of different optical cavities, which are placed in a way that a complex structure is formed, and that altogether, when these cavities are locked, what we see is like the detector to be operational, and that's how we do the gravitational wave astronomy. These cavities, we call them degrees of freedom of the detector. So in a dual recycled interferometer configuration, what we have is like 5 different optical cavities, and all of them have to be precisely locked to a certain accuracy in order to achieve the sensitivity that is required for the gravitational wave sources to be detected. So here we can see that this figure which represent the, so just to mention that this is not to scale. The arm lengths are of course 3 kilometers long. This is just a pictorial representation. Yeah, so all these cavities have to be precisely logged, and the precision accuracy is mentioned in the table where we can see that the different degrees of freedom in terms of the distance, displacement, how accurately you have to log them. So traditionally what we do at the present, this particular cavity which is found in this SR, which is single recycling mirror, is not there in our gravitational detector, but in future we are going to have this new cavity also. And how do we do the locking of this interferometer is we are using the Virgo main laser, which is a single frequency 1064 nanometer neodymium laser, and we are drawing different optical beams, and then we try to generate these radio frequency control signals which allow us to block the cavities. So if you look at the case here, we need to generate 5 different control signals, and their separation in terms of frequency is very wide, so it poses a difficulty in reaching the optimum working point for all the cavities together. So the idea in future will be to somehow reduce this dependence on a single laser frequency. Instead, we have to introduce a new laser frequency that is like quite far away in terms of frequency from the Virgo main laser, and that can allow us to achieve the optimum working point for all these degrees of freedom. So in that scenario, the plan, which is like virtually disentangling the arm cavities, which are fabric cavities in our case, and we should be able to lock them on a different wavelength. In this case, we have this green laser beam at 532 nanometer. So it is like in terms of frequency, it's quite far away from the Virgo main laser itself. So this allows us to reduce our reliance only on the single laser frequency. So in this kind of approach, what we will do is we will try to log the arm cavities with a different wavelength, and the rest of 3 degrees of freedom will be still locked with the Virgo main laser. Now, in order to implement such a case for Virgo environment, what we need is like there can be 2 kind of approaches which one can evaluate. One of the solutions can be to have 2 dedicated laser units that has to provide us the necessary laser beam to implement the control signals. In that case, what we need to do is we need to consider the cost of the system itself, because these stable single frequency lasers can be very expensive. Like if one has to buy 1 watt of laser, it can easily cost you more than 30,000 euros. And the second thing is like these 2 new lasers have to maintain, this green beam has to maintain a constant phase relationship with your wave with this red beam, which is the infrared laser beam. So these 2 stringent limits make this kind of approach more difficult, because in this case, when you try to implement these phase locking techniques to lock 2 laser beams, if your locking scheme is not efficient enough, you can introduce some phase noise in your system that is an unwanted noise in your system. So the other approach can be to, instead of employing 2 dedicated laser units, we can simply withdraw a part of the optical beam from the Virgo main laser. We can optically amplify it, and then we can try to generate the second harmonic of this main laser beam, and that we can use as auxiliary. So a bit of nonlinear optics, that is eventually the phenomenon which we are using to generate this green laser beam. So in nonlinear optics, what we have is like when we try to apply electric field across a material, what happens is like the induced polarization is not only dependent on the linear part of the electric field, but also on the higher order terms of the electric field component. So in this way, there can be harmonic effects in optical regime that can allow us to do frequency conversion. So just to give you an idea, that for a second harmonic generation, which is a second order nonlinear effect, we can produce the green laser beam, which is the second harmonic in terms of frequency of our Virgo main laser. So we call it at 2 omega. Omega is the frequency of the Virgo main, the main laser source itself. This 2 omega is the frequency of the new laser beam, which will be produced in the nonlinear interaction. So we can have this equation that gives us the overall power of your second harmonic beam that can eventually be generated in this nonlinear interaction. So there are a couple of parameters which has to be taken into account. First of all, the intensity of your fundamental beam. So the power of your fundamental beam. Then we have this void refinement factor that eventually takes into account the phase mismatch parameter and the focusing parameter for your laser beam inside the crystal. So if one has to realize the interaction, it can be thought of as like if you have very strong pump field that can go through a nonlinear crystal, and what you can have is the second harmonic, the fundamental beam itself, and the second harmonic of your fundamental that can be generated. So when we talk about this kind of interaction, it's not only the intensity of your fundamental beam, but also the relative phase between the interacting waves inside the crystal. So one has to take into account that your phase mismatch between the interacting waves must be as much low as possible. That can only guarantee you the optimum conversion efficiency. So here in this figure, what we can see that two infrared photons can generate a high frequency photon, and this difference is actually this represents the phase mismatching between these two interacting fields inside the crystal. And the reason for this kind of difference between the phase of the interacting field is the chromatic dispersion. That means like the refractive index of your material is frequency dependent. So one frequency, if the frequencies are different, so your beam are going to see a different phase velocity while they are traveling inside the crystal. So technically there are ways that you can try to reduce this phase mismatch, and that eventually leads to optimum conversion efficiency. So you can produce more of your second harmonic depending how much you can reduce this kind of phase mismatch. So one of the prominent ways to do fuzzy phase matching, in which what we do is like we try to periodically engineer the non-linearity of your crystal such that once your fundamental beam sees one coherence length, after that once one coherence length, the non-linearity flips its sign, and what you see is like eventually a field that is progressing, and you can enhance your second harmonic generation. So this demonstration here in this picture, what you can see is like if you do not have a phase mismatch, a phase matching condition, what happens is like your second harmonic contribution inside the crystals are quite random. So at the end of your crystal, what you are seeing is like most of your field. These are just the phases of the complex amplitude. So most of the second harmonic field is just lost inside the crystal that scatters. But if you have a phase matching condition, what you can do is you can align them. The phases can be aligned, and you can have a cumulative field and output which is far better than when you don't have the phase matching condition. So this is the experiment which I carried out. Of course, this will be done in the Virgo environment, where we have to take a pick off from the Virgo main laser. In the laboratory environment, what I did was like to take a 100 milliwatt encode laser. We were taking a part of the beam that has to be coupled to a fiber collimator. So this is all free space optical beam. It couples to an optical fiber. Then we have this intensity stabilization loop where we are intensity stabilizing using an acousto-optic modulator. So that stable seed beam is given to a 5-watt fiber amplifier. So at this port, taking 1 milliwatt of infrared laser light at 1064 as an input, we can generate up to 5 watts of infrared laser light at 1064 nanometer. Again, we have a fiber collimator that allows us to make the beam again in free space, and with some necessary optical components. When the beam passes through the nonlinear crystal, you see that along with your infrared laser light, now there is some green path. So this represents your second harmonic beam. In this experiment, I was able to achieve up to 97 milliwatt of green laser power for an input of 2 watts of infrared laser light at 1064 nanometer. This is just what I explained from the bench. Yeah. So here you can see that when you do not have your infrared, so the infrared you cannot see with your eyes, of course. So this is the path of infrared. It goes through this nonlinear crystal, and at this point, what you see is like your green laser beam is now produced. You properly filter that green beam out, and you try to separate the green beam and the infrared laser beam at 1064 nanometer. So the results were like quite in relationship with what theoretically it should be in this case. So for a given length of nonlinear crystal and for a given focusing condition and phase matching condition, we should be seeing up to 97 milliwatt of green power for input of 2 volts of infrared laser power. And here what we can see is like our experimental demonstration was quite in agreement with what theoretically it should be. Yeah, then we check the laser power stability, which is an important consideration in our activity because you don't want that your laser should be fluctuating in time. So over a measurement of 5 days, what we found that our second and morning beam and the fundamental beam, they were like quite stable in time. Even though there were some temperature fluctuations, but our control loop were allowing them to remain stable. And then this system should be a portable system that you should be able to take them all the way to the end test masses of the Vigo detector, which are 3 kilometers away. So it's just like a plug-and-play system. You can just insert your fundamental laser beam here, and you can take out your 532 nanometer as an output. So in Vigo environment, how are you going to implement this kind of locking strategy? Is you need to take 2 pickoffs. Using fiber collimators, you need to throw them to 3 kilometers along each of the arms. Then you try to implement the bench, which I showed you in the previous slide. So there should be 2 benches, which should give you the green laser beam, and they have to be very power stabilized, of course. And accordingly, as I have shown in one of my initial slides, that the arm cavities, which are the fabricated cavities, will be locked using these green laser beam. So I have
1 minute.
1 minute. So I had to be a bit fast in that because the time was running out. So yeah, yeah. So thank you. Just trying to cover.
Thank you very much. So thank you very much. Questions and curiosities? I have a question.
Yeah.
So since I can imagine the stability is really crucial in this kind of equipment that you have to add on, how do you somehow provide the same kind of stability on the 2 different arms, since they are quite far away? So what kind of level do you have to control of the temperature and other parameters of your system to be
Okay,
sure
first of all, so the Vigo environment is almost homogeneous all across its premises, like if I have to talk about the entire detector. So eventually your environment is going to be almost the same on the 2 arms, the 2 end test masses. Now this power stabilization loop, which allows us to measure a data of over 5 days of measurement, was giving us this very stable intensity stabilization. So what we are looking after is the intensity stabilization. So we can easily rely on this. This is a kind of local power stabilization loop which you have to implement just on part of the bench, which will be implemented here. So it has nothing to do with the rest of your interferometer. So the rest of interferometer, at different points, you have all these stabilization loops, which allows you to log different degrees of freedom to their precise accuracy. In our case, this power stabilization loop will be local, and they will only be implemented on the benches and the end test masses. So somehow they are not dependent on any of the systems inside the detector. And to your question about which parameter, it's actually through an acoustic modulator, we are trying to control the intensity of the laser field which travels through the URM system. Yeah.
Thank you. Thank you. Any other question? Okay, we can thanks again Ivan. And the next speaker will be Anna Priori from the University of Montevideo. Okay.
Good afternoon, anyone. First of all, I would thank the organizer for this opportunity, and then I will talk to you about carbon nanotube polymer composite materials for stretchable electronic devices. We have beginning to work in this field because in the world there was the born of the necessity of the stretchable conductors. For example, both for industrial applications and for clinical requests. In particular, the clinical request from which we have started to work is the realization, characterization, and review application of flexible and stretchable multi-probe devices. For answer to this request, we have a team to fabricate these devices by depositing carbon nanotube bundles by broadcasting on a polymeric substrate with particular elastic and plastic properties. This is an image of our device, and the total dimension of the device is about 6 millimeter width and 27 millimeter long. And the red arrows show the direction of the stretch possibility. And then this is a photo of a rat that have implanted our device. Okay. This is a characterization of our composite materials. In particular, on the image D, we have we can show that carbon nanotube penetrates into the substrate. In fact, they replicate the substrate and they anchorage into the substrate. While in the image B, we can see that after the stretching of the composite materials, the carbon nanotubes behavior is like an accordion. This is a graph of resistance versus number of cycles of stretching that show the reliability of our devices. In particular, we can see that after the 20 cycle, the value of the resistance is stabilized around the value reached at this point. We have done ECM characterization of the interface to better understand the mechanism of the anchorage of the single wall carbon nanotube into the polymer. In this case, we have studied the polyethylene. In the first image, in the image A, we have a layer of we have separated mechanically the upper layer of the carbon nanotubes from the polyethylene, and we can see the roots of the carbon nanotubes that penetrates into the substrate. But as you can see in the image B, where the separation of the nanotube from the substrate is done after a treatment in a liquid nitrogen, there is the possibility that also the polymeric chain go up and go around of the carbon nanotubes. On this slide, I would speak only about of the high density polyethylene. In particular, we can see the upper layer of the single wall carbon nanotube, the region of penetration into the substrate that there is of about 2 microns, and then the polyethylene, the substrate. There is another characterization, but of polypropylene, to show that the mechanism is the same for different polymer. In particular, in the first image. We can see that that carbon nanotubes, that layer of carbon nanotubes is linked to the substrate by these roots that are linked not only the substrate, but to the carbon nanotubes that are covered by the chain, the polymeric chain. These are images of the section of the same sample, and here we can see that the carbon nanotube penetrates into the substrate, and after the strip off, this roughness shows that the penetration of the carbon nanotube is about 2 microns. Also, if the AFM is not the better probe to measure carbon nanotubes, we have carried out this kind of characterization. From the profile of the material of our material composite materials after the strip off, after that we have removed the upper layer of carbon nanotube, we have that the profile give an average dip of about 115 nanometers. To better understand the mechanism of the anchorage, we have carried out also phase contrast tomography, and by this image we can show that the upper layer of the carbon nanotube is uniform, and this layer covers all the surface of the polymer. And in this particular zone, we have highlighted some routes that carbon nanotubes make with the substrate. In particular, for our device, our Neuro device, we have chosen to use the polyethylene, both for its biocompatibility and for its viscoplastic properties. And from this characterization, we have seen that from the polyethylene, we have after the strip off, we can remove the small quantity of material deposited. I try to summarize briefly how we realize our devices. First of all, we make 6 or 5, depending on the number of electrodes that is necessary, and with the pulse laser ablation, we make these apertures on a polymeric film, on a polyethylene film. After we put this film on a cylinder, and we cover this film with a stencil. In this case, to have 6 tracks of carbon nanotubes. At the center of the cylinder, we have a hole where we put an electrical heater, so we can the temperature of the polyethylene increase, and around 18 degrees, we deposited by drop casting our suspension of single-wall carbon nanotube with ethanol, water, and SDBS. After the deposition, the device, the film, reached the temperature near its melting temperature, melting point. And after repeat this procedure for 3 times in order to obtain uniform and compact tracks, we can analyze our device. This is our device without a connection. This is from the carbon nanotube side, and this is an optical image of the device, but from the polyethylene side. And in particular, these are our electrodes. In fact, in this slide, I show the same image and also an SEM characterization of the electrodes. This is the electrodes, and we can see that nanotubes are compact and uniform. And from this image, we can see that this diameter is about 15 microns. We can go down with the diameters to work with the upper frequencies. And we have done these for another device. This is the in vivo application of our device, and in collaboration with Neuromed Research Center, that is a neurological research center and hospital, we have implanted our device on a pretty moving laboratory rats. This is the response. This is the response of the implantation of our device. This is a graph of the impedance versus days and weeks after the implantation, where we have a spike only in the first week after the implantation, and this is the response of the brain tissue. While in the second, image is the recorded electrocorticograph signals, and we have implanted, in particular, this device for about 3 months. So we had electrocorticograms for the first week, the 15th and 11th week. These signals are comparable with that we expected. This is a short movie of our rats. This is the connector. This is the connector from which we connect the device from to an output, and this is the rats during the recording. Okay. From the histological analysis, we have shown that there is no toxicity for our device. As I told before, we have done also the device with platinum, but as we can see in the first image, the difference is that after stretching the device, while the resistance of the tracks of carbon nanotube increase, but increase after with a bigger stretch, the resistance of the track of platinum increase for a little time, but then the tracks is broken. And these are two images of the device of carbon nanotube and platinum after the explantation. The carbon nanotube don't have dispersion into the brain, while the platinum there is on the device. So, in conclusion, with our characterization, we have shown that the anchorage of single wall is very harder and is about hundreds of nanometers. And then, with the electrocorticogram recorded during in a period of 3 months, we have demonstrated that this kind of device is more useful and is more useful for the neurological application. In fact, we aiming at brain-machine interface and other different applications, not only into the clinical field. Thanks for the attention.
Thank you very much, Anna, for your presentation. Any questions or curiosities?
So thank you for the nice talk. You tried in vivo your stretchable electronics built with carbon nanotubes basically, but I read a few articles in which the authors claim that carbon nanotubes are actually toxic for the living being. They could destroy the liver of a living being. So,
No,
how do you treat this?
no, the histological exam has shown toxicological exit. In fact, we have seen also from the strip-off test that we can strip off only an upper layer, but the carbon nanotubes of this upper layer are linked to the carbon nanotubes that are penetrating into the substrate. And while the bond from carbon nanotubes of the upper layer are weaker, the bond from the carbon nanotubes of the upper layer and that are penetrating is harder, and it's difficult to remove all the carbon nanotubes.
Any other question? Okay, thanks again, Anna, for the nice talk. And the next speaker will be Alessandro Delia.
So, good afternoon to everybody. I hope everyone is still awake. This is the last talk of this session. So, I am Alessandro Delia. I'm a PhD student of the University of Trieste, and I'm here to talk to you about the synthesis of vanadium oxide nanostructured thin films, and I will show you an electronic characterization as a function of the oxidation state, using straight electron spectroscopy and absorption spectroscopy. So, first of all, why nanostructured thin films? Because nanoparticles have a galaxy of applications. You can just pick one, and with some nanoparticle you can achieve some of these applications. So in particular, I focused my attention on the synthesis of nanostructural samples with tunable oxidation state. Why this? Because tuning the oxidation state, it means tuning the electronic properties of your sample. And the electronic properties of your sample are of fundamental importance in a lot of applications that involves, for example, charge transfer at the interfaces. So, in particular, I focused on vanadium and vanadium oxides, since vanadium is a very reactive element and it can form a variety of oxides which can be used in very interesting technological outcome. For example, vanadium pentoxide can be used as a cathode for lithium-ion battery, and the vanadium dioxide undergoes a metal insulator transition, which is reversible and which nature is still under debate, literally. So this is a brief outline of this presentation. I will start talking about the nanoparticle source. Then I will show you how we can control the oxidation state of our sample. I will show you an investigation on the electronic structure through Auger spectroscopy, and then I will show you that we can produce nanostructured thin films with tunable work function as a consequence of the oxidation state control. And finally, I will show you preliminary results on the morphological and structural characterization of this field. So, very quick, I used a pulsed microplasma cluster source that is made up of a ceramic body in which is inserted a metallic cathode. These cluster sources work in this way. We have a pulsed bulb that injects a puff of a carrier gas, and a synchronized electrical discharge will ablate the cathode, creating a confined plasma that will erode the cathode, producing the nanoparticles that will be carried away for aerodynamic effects, basically. We can create oxide nanoparticle adding a small amount of oxygen inside the carrier gas. And we proved this using in situ photoelectron spectroscopy. So, for any one of you which is not in condensed matter physics, photoelectron spectroscopy is a technique which involves, of course, a photon beam. This photon beam will be enough energetic to remove an electron from a core level. So we can record this, the kinetic energy of this electron, which depends from the energy of the photon beam and from the binding energy which it had inside the solid, of course, and also from the work function. So this technique is surface sensitive and most importantly give us information about the chemical state of our sample. So in the left graph are depicted the vanadium 2p and oxygen 1s spectra. So you can see the shape is changing, and to obtain quantitative information from this spectra, I used a fitting procedure. In this way, I was able to isolate the vanadium component, which are linked to different vanadium oxidation states. Making the ratio of the area of these components, I was able to extract the stoichiometry. So using the cluster source I showed you before and doping with oxygen, I managed to produce vanadium oxide on a structural film tunable oxidation state. So tunable oxidation states, I told you it means tunable electronic properties, and in particular electronic tunable valence band occupation. And I proved the valence band using Auger spectroscopy. So the Auger decay is a particular kind of photoemission process, which is the consequence of direct photoemission. So with direct photoemission, we create a hole in a core level, and the system, of course, is not stable, and the surrounding electron will try to cover this hole. So, for example, in this picture is depicted the Auger decay 2p, 3.5, 3p, and valence, since we have the direct photoemission hole in the 2p and 3.5 level. Then the electron that will cover this hole is inside the 3p level, and the proper Auger electron will be ejected from the valence band. So, following this decay channel, we can actually have a probe of the valence band. And respect to the direct photoemission, Auger spectroscopy and Auger electron have the feature that they have a constant kinetic energy, since the kinetic energy of the Auger electron depends only from the binding energy of the electrons involved. So, oxidation state is proportional to the number of unpaired 3D electrons in a vanadium oxide. In this graph of stick and balls, I depicted the electronic structure of the valence band of vanadium dioxide. So we see we have one unpaired electron and some other electrons which are bounded to oxygen 2p electrons. So looking at the Auger 2p, 3.5, 3p, 3d, we see that as a function of the oxidation states, there are two features that using all my imagination I called A and B. That evolve with the oxidation state. So I was able to link the A feature to the electron, to the 3D electron of vanadium which are bound to oxygen, and the B feature to the unpaired 3D electrons. Again, fitting these two features, I was able to extract quantitative information, and in particular the ratio of the area of the B feature respect to the sum of the A plus B feature is the percentage of unpaired 3D electrons in the sample. As you can see, this quantity as a function of stoichiometry can be fit by a linear relation, and the particularity is that for stoichiometry 0, which means without oxygen, the fit goes to 1, since all the unpaired electrons are unpaired. So all the electrons are unpaired. There are no oxygen available to bond. So the A contribution is 0, and then we have B over B, it's 1. But for the maximum oxidation state, we shouldn't have unpaired electron, and but we actually have a value which is 0.2, which is a fingerprint of a strong vanadium thread oxygen to be hybridization, and it points out a failure of the ionic picture to describe vanadium oxide valence band feature. Then very quickly, I show you also that we tuning the oxidation state. We are also able to tuning the work function as a function of stoichiometry. The work function is the energy which separates the Fermi level from the vacuum level. So this is a very important parameter in all the applications which involve charge injection at the interfaces. Since basically tuning the work function, you can tune the Fermi level. And we see from this graph that our experimental point, which are the black dots, are actually systematically higher respect to the bulk analogs, which I took from literature. This is because since our samples are nanostructured, which means that they are formed by nanoparticles, there is a strong quantum confinement effect which enhances the work function. And using this relation that Zhu and Zachary have found in literature, we can also extrapolate the diameter of these nanoparticles. So you can see as a function of the oxidation state is between 2 nanometer and 1, more or less. So, but electronic structure is not everything. So it's also important the crystal structure and the morphology of the nanoparticle. These are important parameters when we talk about nanoparticles. So this is a TEM images with a low magnification. You can see that the nanoparticle I produced, they assemble in these dendritic-shaped agglomerates. And if we go deeper with the magnification, we can see that these nanoparticles they exhibit a fractal aggregation. This means that single nanoparticles come close one to another without a precise shape. And so we can also see from this image the atomic planes of the nanoparticle that could suggest that our samples are crystalline. So in my experience, one should not trust blindly of microscopy, since especially for high magnification, it can modify some feature of your samples. For example, performing absorption spectroscopy. Oh, sorry. Absorption spectroscopy on our sample, we see that actually our samples are not crystalline. For example, okay, sorry, if any one of you is not acquainted with the absorption spectroscopy, it works in the sequent way. So you enlighten your sample with a photon beam, and you pass across the resonance of your sample, and in this way an electron is removed from a core level and is placed in between the Fermi level and the vacuum level. It means it's put inside an unoccupied level. So this technique is chemical selective, and it gives us information about the electronic and the structure of the crystallinity of our sample. Again, in vanadium dioxide, we have, in vanadium oxides in general, we have vanadium L edges and oxygen K edges very close, which means that vanadium 2p electron and oxygen 1 electron are very close in binding energy. And we can see that studying a crystalline sample of vanadium dioxide, on the oxygen K edge, we can see that there is a very nice crystal field splitting, which results in two features of the pre-edge of the oxygen K edge. While in the sample I produced with the cluster source, we have some wide bump, which means that the crystal field is not strong enough to have an ordered sample. So in the last analysis, our samples are amorphous. So, in conclusion, I showed you that we can produce vanadium nanostructural thin films with controllable oxidation state. I showed you that using OJ spectroscopy, we can investigate the valence band structure and we can point out some interesting features, and that as a consequence of the oxidation state control, we are also able to control the work function of our sample. And as last I showed you that using this sample, we are able to produce amorphous sample that someone should never trust blindly on microscope. I would like to thank all the collaborators and thank you for the attention.
Thank you very much. Any questions for the last speaker? I would like to ask you what kind of different application you can have working with different oxidation states of the vanadium in this case.
So, for example, in organic semiconductor devices, you have that the active layer doesn't have intrinsic charge carriers. So you have to provide charge carriers through the electrodes. And to provide efficiently these charge carriers, you have to align the Fermi level of the electrodes with the HOMO level and the LUMO level of the active layer. So as much as you are able to align this level, as much more efficient will be your device. For example, in OLED, that most of us have in our
televisions.
Yeah, televisions or iPhone. You have light consuming less power if the energy level of the electrode and the organic in between are perfectly aligned. So tuning the work function, for example, is one essential tool to have efficient organic electronics.
Okay. Thanks a lot. Okay, we have a question from the very last row.
Hello, like you mentioned the control aggregation, do we know like somehow the dimensions of the aggregation, like is between from 2 and 3 or from 1 and 2?
So it's actually between 2 and 3. When I say this between 1 and 2, it was an extrapolation from the equation of the work function I showed you before in this slide. From this equation. But this equation relies on the approximation that the nanoparticles are perfect spheres, which is not the case, of course, since they are this ugly stuff.
Okay, any other question? Otherwise, we can thanks again, Alessandro. Thank you. Okay, we are almost on time. Now we will change for the roundtable session that will be moderated by Elisa Nichelli.
Mi metto in mezzo, sì. Una radice intermezzo.
Probabilmente farò così.
Magari così. Ce l'ha lei delle slide, Sì, li scambiamo, magari lei ha le slide. Sì. Hello everybody, can you hear me? No? Can you hear me? Yeah, now yes. It's a pleasure for me to introduce you this roundtable. Thank you for asking me to do that because it's very interesting. The topic, the link between physics and industry. Our guest today, starting from here, Antonella Delle Noci.
Federica Stella, because Antonella could not attend.
Sorry?
Federica Stella, because
okay.
Antonella could not attend.
I'm sorry.
Sorry for that.
No problem. And you come from HR of ACCA?
Again, sorry. Sorry for this confusion. So my colleague Antonella Delle Noci is a HR partner,
Okay.
but she couldn't attend today, so I'm here as a consultant to overview ACCA, to have an overview for ACCA, and to share my experience.
Perfect. Perfect. And you have a background in physics too. Okay, perfect. So we are all physicists here. That's nice to know. And Daniel Ricci, who comes from PhD in theoretical physics, and now is a credit and counterparty risk manager at Cassa Depositi e Prestiti SpA. Nice to have you here. And Najda Said. She also has a PhD in physics, in cosmology, let's say, and she's the manager of IE team in IBM. Perfect. And just a couple of numbers so that we all introduce ourselves to this topic. I found online some information. A report from American Institute of Physics Statistical Research Center in 2016 tells us that 70% of the potentially permanent initial hires of physics PhD graduates in the US are in the private sector. So it's something important to talk about. And in the last 3 decades, 40-55% of all PhD graduates go on working in the private sector. So it's something that we should talk about. In this audience, maybe a lot of you will choose this career. It's not something that we have to be ashamed of. I am also a physicist and I work partly in the private and in the public sector, so we can do this. Let's start with you, Daniel, the only man at the table. What can you tell us about your experience so far? Yeah.
Okay, first of all, I would thank the organizer for inviting me to this meeting. I'm very glad to see how this meeting has grown during these years. I remember a lot of years ago the first editions. In fact, I attended the second edition when I was a PhD student in theoretical physics, and the second edition in the University of Rome La Sapienza. And then I was also one of the organizers of the third and the fourth editions. Then in 2014, I decided to change job. I was a postdoc researcher in the University of Padua, and I worked on string theory and supersymmetric gauge theory, so a very theoretical stuff. But there were several reasons and it made my decision to change work. Some personal ones. For example, in Padua, I met my future wife, so I wanted to find a permanent position.
So don't go to Padua. The suggestion is.
But I wanted to find a kind of job, another exciting job, such as, for example, the scientific research. There was a friend of mine, another PhD student, and during that period decided to change job, and he began to work to a consulting company. So I began to study mathematical finance, and also in Padua at the university there was a course on mathematical finance. So I attended that course, and it was very interesting because a lot of, for example, stochastic processes, the random walk, or the Ito differentiation as the base of mathematical finance, the so-called Black-Scholes equation, which is one of the most important equation in economics, essentially is the Fokker-Planck equation. So I sent some CVs to several financial institutions, and finally, in 2014, I began to work at Cassa Depositi e Prestiti. Probably you don't know this company. It is a joint stock company, mainly under the public control, in the sense that its majority shareholder is the Italian Ministry of Economy and Finance. It is a company with a very old history, more than 150 years. And probably you know the Italian postal bonds, for example, buoni fruttiferi postali or libretti postali. You probably guess that these are postal instruments, while these are financial instruments developed by Cassa Depositi e Prestiti. And my current job is as a credit and counterparty risk manager, because in a financial institution there are several areas. For example, finance, middle office, back office, the information and technology area, but there is also the risk management, which is very technical area. In fact, a lot of my colleagues are physicists and mathematicians, because this is an area of secondary control, for example, for finance and the other areas, where a lot of financial models are developed or are validated. Our office, for example, defines the limits on credit and counterparty risk. The credit risk is when, for example, we lend money to a counterparty, so there is a loan with a specific interest rate, and this credit risk is the risk of default of that counterparty before the final settlement of cash flows. And this is a unilateral risk, because it is only our risk. While the counterparty risk is a particular kind of credit risk, where the underlying instrument is a particular product which is called derivative. For example, an interest rate swap, which is booked, for example, when we have a loan. For example, we have a loan with a fixed rate, so we have a risk, an interest rate risk, because for example, related to the market movements of the interest rates. So we want to change the fixed interest rate of the loan to a floating interest rate. So we enter into the so-called interest rate swap, which is a particular product with two legs, where one leg essentially reproduces the loan, while the other leg is the floating leg. And the value of this swap is defined by its market value, which could be positive or negative. So it is a bilateral risk of default. In the office where I work, I can apply every day all my technical skills. For example, during the university I learned how to program by C++ or Fortran, while in custody positive recipe we usually use Python as a language of programming. Now, for example, we are currently trying to apply neural networks or machine learning for evaluating the credit risk. We wrote several scripts in Python or in PySpark, in several languages, in R language, or we use several programs, for example, Gradle, for analyzing historical data. Not only our area, but also, for example, in finance, you can find an exciting opportunity of work. So you could, for example, take a look to our website where there are a lot of open positions. I think that for a physicist or for a mathematician, the scientific research is the primary job, the primary decision. But if you decide to change a job and to move to a company, there are a lot of companies in Italy, but also abroad, where
I see big smiles somewhere. You give us hope. So, is there something you're missing from research?
Well, about
the job.
Well, I think now it's all very fast, in the sense that when the broadcast something, it must be done very quickly and in a precise way. Sometimes I say, if you want something fast, I can do that in a bad way, or if you want something done fine, I must take my time. While during when I was a researcher, I could do my research very.
Unless you have to write a proposal. As far as I remember, proposals are done in the last 5 minutes before the deadline. Usually. And thank you. And we will have a huge part of question and answer after. So I will give the mic to Nasla and ask you the same question. So, what about your experience with this other environments?
Okay. Again, first of all, thank you for inviting me here. It's a very big pleasure to be here and to talk with you because I was there a few years ago, some years ago, not few, and well, I think you can imagine why I choose to change work. It's something very similar to him. Yeah, you're right. It was a mix of money and the ability to stay somewhere fixed, no? And the idea to build something and maybe not change place every year or stuff like that. So this is the main driver that made me say, okay, I love research. I really was passionate about what I was doing. I was working in cosmology, so I studied the universe and dark matter, dark energy, neutrinos, so it was very interesting, really. However, I decided that I need to be sure about my future, and so I took this decision. And it was a very difficult decision, a very tough decision at first. However, I was always been very interested also in informatics and computers, both on software and on hardware side. So the first place I thought was IBM, because IBM is the company of many big high-performance computers, because IBM invented a lot of technology in the years. So I just tried to send my CV and say, okay, I would like to have a job there. And the first outcome was that I signed up for a stage position, an internship. And they told me, okay, not the PhD is too much for this position, so we cannot accept you. I said, oh, what? But it is,
so you have time to stop. Stop thinking about the PhD.
Don't worry, really. You will have time to send it back. But at first I stayed just like, oh my God, what? And however, I was very lucky because they needed a person very soon with the cloud skills. I didn't have any cloud skills, so I went there to have my interview. They told me, well, tell me what you know about cloud. I said, okay, I can do SSH to a machine that is remote. This is what I know about cloud. And they said, okay. And I said, but I am quite smart, I think, and I can learn very fast. So if you trust me, I can put myself in. And they trusted me. And I started to work there as a cloud technical sales. I didn't know anything. The first day I went to my job, I said, I don't know what I'm going to do. However, it ended up that fortunately it was something that was very technical. So it was at least at first very separate from the business side, because really I didn't understood anything about that. I see the salespeople talking about money, income, revenue, and I said, really, I don't know what you are talking about. But my work was very, very technical. I just needed to design solutions for the customers. So it was something that was interesting because I didn't know anything, so I needed to study, to learn new stuff. And it took me up. After some years, I can say that IBM was a very good choice for me because I didn't know that at the time. I could imagine, but I didn't know in the way I know right now, IBM has a very huge research part. Not here in Italy, unfortunately, but there is a very big business unit in IBM that is totally dedicated to researching new stuff. So even if I don't work in IBM research, we have access to a lot of information and a lot of, for example, I love computer, I love physics, I am naturally passionate about quantum computers. So we have access to all the resources about quantum computers in IBM. So this is something that keeps you alive. Even if it's not your work, you can always find a way to grow your interest in other parts. And with this kind of interest, I can go around and, I don't know, in the university, have lectures with the students. So in a kind of way, I am trying to be very tied to the old job that I had. And this is the good part. The other part is that there is a business, and so you have to answer to the business request. So you have to do also your job, but inside this, if you can manage the time that you have, you can go around and explore. And by going around and exploring, I moved from cloud to data science, because it's something that is clearly much more near to my past, to my education. And so in few years now, I am in IBM from 5 years more or less, or enough. So I started to get interested in this, and right now I am managing a team, but I am part of the team, so I will my team in this sense. We are physicists and mathematicians, and we just work very hands-on on some pilot and innovation projects, so to say. So finally, I found something that is in a very wide sense related to what I studied, and I feel quite comfortable for now. However, I cannot deny that I miss the research sometimes. So IBM helped also in another thing that is very important for me, is lifetime. In research, when I was a PhD student, I will decide, okay, today I will wake up a little bit later and maybe work also later, but manage my time in my way. Not all the companies will be like this, unfortunately. IBM is quite a good choice in this sense.
Perfect, thanks. So this kind of job lets you grow and continue learning. This is something I
absolutely.
Okay.
That is the most important part. Otherwise, I would get bored.
Because I think that's something that is misplaced in this kind of topic. A lot of people think that going private means steady job, all the same every day, and boring.
Not everywhere. Let's say like this. Okay. You can find places in which you can balance both your interest and the job you have to do. So
okay, thanks.
You're welcome.
And now, Federica Stella.
Yes.
You are at ACA,
yes.
And you have a presentation.
Yes.
We have the...
This one.
Okay, perfect. You have everything. So
okay.
Tell us about ACA.
Okay, thank you. So thanks everybody to have involved ACA here today for inviting us and myself as well. So I am a physicist and I am a consultant in ACA. So now today I will just introduce you ACA very shortly, and I will share with you my experience.
Yep.
Okay. Okay, so this is the very short agenda we propose. So I will show you some slides about ACA. I will share with you my personal experience, and then I will just spend a few words what it means being a consultant. Okay. So ACA is a product company and also an engineering consultant company as well. And is present in most of the phases of product life cycle, starting from research and development up to aftermarket with different skills, starting from system engineering up to consulting, information system, and so on. We are about 20,000 people spread in 23 countries all over the world, and the 2018 revenue was about 1.5 billion euros. Okay, this is a short slide, this one and the next one, to present you the ACA presence and the revenues by business segment. Basically, ACA is present. Okay, ACA is presenting different sectors, ranging from automotive, healthcare and life science, aeronautics, space and defense, railways, oil and gas. And today I just highlighted the part relevant to aeronautics, space and defense because I'm currently belonging to the space business unit, and so I can. Okay. Yes, and again,
this one.
Is it? Yeah, thank you. I pointed wherever. Okay. So one of the main features of ACA in the space division and the frame of the space division is that ACA is present in all the three segments relevant to space, meaning ground segment, space segment, and launchers. Okay. As I said, I am a physicist as well, and I'm happy today to share with you my personal experience. I fully agree with her when she said the reason why she decided to leave. Okay, so I gained my master's science degree in applied physics with a focus on optoelectronics here at Tor Vergata. And then, since I was passionate about research, I decided to continue with the PhD. And I gained my PhD in microsystem engineering, and I work with microfabrication processes, merged with the competencies again in optoelectronics. And I was really in love with research, and I would never leave it. So at a certain point, I start asking myself, at the end of the PhD, I gained a lot of skills. I acquired a lot of competencies, technical, experimental, also relevant to management of documentation, and also soft skill. And I said, which of these competencies could be of some interest for private companies? Because I was, as she said, I was a bit scared about outside world, because you say, okay, I'm doing a lot of things, but maybe nothing that is relevant for the outside life. And so, as I said, I continue with some research grant, but at the same time I start looking around. And then, as a result of a collaboration I had in the past during the PhD years with a group, I knew that there was a semiconductor company that was hiring in north of Italy, and so I decided to apply. The position was test development engineer, and when I arrived for the first interview there, okay, the place was plenty. It was plenty of rooms, plenty of whatever relevant to electronics. So there were boards, cables, testing machine, and I say, okay, maybe I'm in the wrong places. So I was quite sure that because I was having my interview, and there were other 3 candidates, engineers. So I say, okay, electronic is not my field. Maybe I will not be selected. And then I was surprised because among the 4 candidates, what made the differences was one of the competencies that I acquired during the physics, my master's science degree in physics, and they were quite happy because they say no one can reply to this one. Every time we ask, you have been the only one that, and so it was quite fun and that. So I started working there, but I didn't do anything in principle. And then at the end, I discovered that most of the way of reasoning that I acquired during my years was the key to perform my job. And I started programming C, C++. I was designing the electronic board. I was developing the code for the testing machine for these semiconductor devices. And also I was producing all the documentation relevant to the final delivery. So at the end, I didn't have any specific competence for that job, but at the end of my head, there was the result of physics years of study, was what helped me in performing my job. And then this was a company or product. Then for personal reason, I needed to move back in Rome, and there was an opportunity in Arca Technologies. And so, coming from a product company, I was a bit scared also about the fact that I didn't know very well the consultant company and consultant process. And so, when I applied, again, I changed completely my job. And this was another aspect of the integration of physics in the private company, because at the end I was coming from a test development engineer position, but Arca selected me for being a quality assurance in spacecraft assembly integration and test, so a completely different job. Again, I started from scratch, and I realized what is the main difference now from the product company and a consultant company, because in a consultant company you have the opportunity to play several roles and to work in different projects. I had the opportunity to work in three different space projects with different roles, completely different from each other. And I can say again, all the knowledge I acquired during my years in physics helped me, because at the end I can say that I perform research every day, but in a different way. You will always find something that intriguing you in your job, because your head is organized in that way. And even if as she said, I was a bit upset to leave the research environment, I can say that yes, after 10 years, the things that I miss most maybe is the fact that but this is a very personal experience. I'm not more so close to technical aspects, but this is, this is just very related to my life. But I can do it myself outside the job if I want, and also the fact that I work in the space division, however, allows me to highlight some topics that I can follow myself then. Apart from my specific job, so I hope to have been. So just a few words about the fact to be a consultant. Here there are reported just a few numbers, but the core of the consultant of a consultant company is that you can do your job for a single company, but at the end. With your skill, you should do your job for different customers. So meaning that instead of have a very vertical knowledge, you will have a transversal and cross competencies that will allow you to meet and to know very different reality. And basically, in terms of pro and cons, so I can say that. The first point is the flexibility. The consultancy allows you to have to meet the dynamic work environment. You will never work on the same. Sorry, finish with the. Sorry.
This is problem solving.
Okay. So you will never work on the same project. You will always change, and maybe you will be asked by customer to implement a new solution from scratch. This is something real interesting, just because customer ask your company to say, okay, I need to develop something new, so I will ask professional help. And in terms of cons, flexibility means also to have not a constant workload, meaning that your workload is depending on the customer, and this is not negotiable. So maybe starting, you could have some more relaxing point maybe, but then you will have to manage high peaks because it depends on the request of customer. And the bids, if you win some bids, it is not predictable, let's say. Okay, in terms of cross skills, again, as I was saying, maybe this is the important point coming from the physics environment, meaning that at the end of your course of study, you have cross skills. These are helping you to work even to end-to-end solution, meaning that you will be able to perform a different role on the project. So this is a process, but then in terms of cons, this means to face always new challenges and also to be continuously trained on the job. Because as you see, my experience is starting from a test developer, engineer, and then I moved to quality, and then I moved to database administrator. So it's something demanding. But and then also soft skills are very important because, as I said, when I was working during the PhD, mainly during the PhD, I was interacting with several groups for my thesis, and then this really help you in the private work because you will have to interact with different roles and different management lines, but also this means the relation with customer is the most important part because you will have to manage communication because you will represent your company to the customer. So you will be asked to be able to manage also stress situation related to the project progress. And so this is one of the cons, the part of the stress. So I hope to have been quite fast and quite clear.
I would say yes, and thank you for your contribution.
Thank you.
As you all have seen, we have a lot of similarities and a lot of differences, of course, in these private jobs. So I will now open the microphone for questions because I think that there will be a lot of them.
First of all, thank you for such a nice discussion because as researchers, we never get to know the other side of the market and the industry, what is happening there. So very nice talk by all of you. I think it's nice that you have included stress in the cons, but I think we also have stress in the research. But my first question is to Najla. As a cosmologist, I mean, in the field of cosmology and jumping into a completely different way of utilizing those skills, because the kind of freedom that you have in research is the universe is not demanding, but here the market and the product and the customers are demanding something from you. So, what kind of difference that you feel as a from the research life to the new market life? What things that you find it different from the research point of view?
Thank you for asking. Oh, I think I made it done. Okay. Yeah, there are a lot of differences. I won't lie. It's a completely different job. You don't decide by yourself, but anyway, during my PhD, I never totally had the chance to decide by myself. So, in a sense, I was quite. Not so completely similar, but there are similarities. However, what she says is very important. You have to answer to customers, and customers are your first priority in every way. However, when you, I don't know why, but I feel very committed to my customer, and this is something that push me to do my job at my best. And in a sense, when you work with a customer at 36 degrees, so you follow his industry and his business needs, you make research in some way, because you have to understand what can be useful to your customer, and for this you have to study, you have to go and learn what is happening in the industry and what is happening to your customer, who are his competitors, and what technology you can employ and how in order to help them to succeed. Okay, so it's not the same, but you can find a similar way of working. You can find a way to create a trusted relationship with your customer in which you become a partner. So you work together, and when you deliver a good solution to a customer, at least you are very happy, as when you submit the paper for which you work a lot. So it's very good, the same, and you can make a research work, you can make a kind of conference when you go to meeting and you have a customer, the management of the customer, the other management of the customer, your manager, the manager of your manager, and so on. It's a little bit similar. You can find the right similarity to make you do your job at best.
Thank you so much.
However,
I have another question to Antonella.
Federica, sorry, Federica.
So, how it is to work, I mean, since you are Italian and working in Italy, that means that Aqua Technologies, is it open to also English speakers if there is a possibility to work in Italy? Or are there chances that they also take recruitments in other countries as English speakers?
Okay, thanks for your question. Of course, as I said, we are an international company, so there's the opportunity to work here in Italy, but in other countries as well. We are spread in 23 countries around, included Europe, and here in Italy we have different premises. We are here in Rome, Milan, Turin, Bologna, Pisa. We are very well distributed also on national territory. So, and of course, this means that as an international company, there's no any constraints relevant to languages. And if I correctly understood your question.
Yeah, I just wanted to ask from the sense that whether an English-speaking person can apply in Italy, and there's no language constraint.
No.
And, since it's a large domain consultant-based company, I don't have to ask about the financial satisfaction that the company provides. Right? Your smile tells everything.
As she was saying before, one of the main drivers in my experience to leave the research was relevant to the fact that I wanted to buy a home, honestly, and so I was not sure that in continuing doing research I would have reached my target.
You're secretly answering the hidden questions in our mind. Thank you so much.
Thank you to you.
Any other question? Yeah.
I have a general question to everyone. If you ran the company working, which position you would prefer, a PhD instead of a somehow experienced master student, graduate, or graduate student?
Okay, thanks for your question. So, in my view, I would say there's no a strict correlation between the degree, but the relation is done in terms of competencies. So it depends on the current requests we have from customers. Maybe sometimes it happens that we have the need of resources very well skilled in C and C++ programming, or maybe it depends on the customer request. So it's not strictly related to the PhD. And I would also say that today we have here, I have with me Francesca Remarchi. She has a PhD in astrophysics, and she started a stage as an internship in ACA 2 months ago. So again, this is a well representation of the possibility we have, because she wanted to know the private company way of working, and ACA offered this possibility just to taste what does it mean work in the private sector. And I hope she is satisfied for the time being.
You're of course free to say no. and stop your internship tomorrow.
Okay, so I hope to have a reply to your question, at least.
So you actually see no strict correlation between having a PhD and the position you can occupy in your company?
Yeah, because basically what it is, our process is basically related to the production of a dossier of competencies that you provide when you apply to maybe to a single position or even to a website. And this dossier just include all the competencies you have. And then there's a match in terms of competencies and customer requests. So maybe whether, I mean, sometimes, as I said, programming, but maybe project management competencies, or maybe mechanical integration. This is some of the example I had in mind, but as I said, we work in many sectors, and so really we have huge opportunities.
Any other suggestion? Okay.
I have a question from the side of the university. Since I also have some of my students here, I would like to know from your side, how can we boost somehow to meet the requests of the companies and the needs that companies have, and how we can provide the competencies that you need from the student side. Also, from the point of view of what you have just said, that not always the PhD is what we want. So maybe there are some students that are interested in searching for a job position in the companies just after the master degree. So how can we boost up this the meetup of these two sides?
Okay.
It's from all of you.
Okay. In my view, maybe the way. Okay, we had some weeks ago. We had a presentation and a meeting for the School of Aerospace Engineering, and so the questions were very similar. What I would say is that, in our view, the way to boost this request is to have a mapping. For instance, I would say to apply to the website and to specify through the form your competencies, because keywords are used to doing the matching between customer request and the profile. And then after this first step is done, we call the person for the interview, and during the interview we'll also have the chance to meet also and to know the soft skill of the person, and this will be a plus in order to vehiculate and address the resource versus the customer request. So I would say zero order step would be the application to the form online, and then this, I think that today is for sure an opportunity to have, in this presentation that I will share with you at the end, I mean, I will distribute to you if you want. We also have the contact of a relevant person of HR and the business unit manager. This could be a straightway opportunity to share information about your competencies and your willingness to do a job outside the research.
Just to add something, then I would like to hear also something from you. But could it be useful to have some kind of platform from the university side in which we show the general soft skills and competencies that we provide for all the students, basic level that we ask the students to have at the end of their career as a student, and maybe some specific skill that they have on your own. Maybe it could be useful also to boost up their specific skills some way, I don't know, apart from the standard courses that we have, just to have more variety in the skills that they have, because somehow we tend to give to the students the same kind of skills as a basic level, but maybe we are not stressing enough the personal skills that maybe you are searching for.
Okay, so if I understood correctly, you are saying maybe to implement something here at the university in terms of courses, more focus on what is the request outside. Okay, okay. Yes, this could be, of course, an interesting aspect that could be faced together. I mean, we should dedicate some time to have a deeper insight on that. This could be for sure really helpful. We did some, but again, it was on ACCA side. You are saying now on your side, but at the master of Francesca, help me. Sorry. Yeah. Thanks. I didn't remember. I'm starting to mix it up. So we had also one class here to explain in the specific the current activity that Francesca is doing, just to provide again a deeper insight on one topic that is one of the activity currently ongoing in ACCA. And maybe yes, we could work on both sides on this way to try to match and to clarify which are the aspects that need to be stressed here. Okay, I will take a note and then we can share some other words later on. Okay.
Okay. If I can intervene, yes, you're right. Usually big companies make a kind of a stage of internship for graduate students or graduating students. And in recent years, we are seeing also another thing that is a mixed PhD. So you can do a PhD that is both in the company and in the university. We have, for example, in the field of quantum computing, there is a field that is expected to grow a lot in the future. We have no competencies at all. And I have a colleague that made his PhD in the University of Pavia, if I go right. And however, he's a colleague in IBM, so he had the opportunity to take a PhD, but in the same time of work inside the company. So we are seeing a kind of, let me call it hybrid education that is growing. I think it should not be the only education. I think research should be separated from the industry, but with my experience, I think we should give a choice. You can follow up on pure research, but if you are then interested in go somewhere that is not a research field, probably it would be good if you are educated from the start, also to other things that will make the difference in your work.
Yes, you also, sorry, did you want to say something? Okay, yes, you also remind me that, as I said, when I started to work in Pavia, yes, this was the result of a collaboration we had, because at that time, during my PhD, there was a company, in this case was ST, Microelectronics, that was doing some classes in our university, and I was asked to do for students the technical part of this course, and in a clean room environments and so on. And as a result of this collaboration, I met the outside market of the semiconductor industry. And then this guy that asked me to do these classes, then told me when they were not their company, but another one was looking for a test development engineer. So he said, when I asked, okay, what I can do outside, he said they are looking for that. So maybe also to have some specific classes dedicated to external companies that could provide some insight on the activity. This could be maybe one option.
Okay, I think that PhD students have all technical skills to work in a private company. What I think they don't have is first of all, they don't know how to do a job interview. For example, I remember my first job interviews. I was completely shocked because I didn't know what to say, what to stress. So I think that if the HR, the different companies could give some advices to PhD students, it would be very useful. For example, how to write a CV, what to write in a CV, because this is the first thing that the HR read to understand, to select a candidate with respect to others. So I think these are two important stuff.
I think we have time for one more question, if there is any. Are you sure? It's kind of a unique situation here. Okay, so I would say thank you to all our speakers, a big applause. I think now, Luca, we have a very interesting poster and wine session.
We do have a poster and wine session where we have the lunch, so in the same area where we have the lunch. All the poster has been moved to that area, and you will find wine as well, so we can discuss drinking wine. Thank you.